Okay, so here are the notes on section 2.2. So just like we talked about in class, you learned that arithmetic sequences are kind of like linear functions, similar, and that geometric sequences are basically like exponential functions. Okay, so just some examples just to like show you the two things. Remember how you have like an equation of a line, right? So an equation of a line like this, it has a y-intercept and a slope. Well, that's the same thing as like your initial value and your common difference here. So you can think of, you already know how to write the equation of a line because you know like, hey, it starts at 8 and it looks like it's going down 6 every time. So if you knew that about a line, you would write 8 minus 6x, but in our case, we're writing n, right? And if you got told information, like you're basically in this situation, you're kind of being told a point, right? And over here, you're being told the slope in a way. So look at this format right here, the slope-intercept form that you knew, or the point-slope form that you knew. Now you're used to seeing it like this, like y minus y1 equals m and x minus x1. So notice that this y1 is just brought over to the other side, right? And so look how that looks exactly like that. Okay. All right. And so basically what you can do is you can say an, you can use that negative 10 because that's like basically a y value like over here. And so you'd say negative 10. The slope is negative, so instead of putting plus, I'm going to put minus 6. And then in here, I'm doing x minus x1. So I'm keeping my x, which is really my n value right here, and then minus the x value, which is really the 3, which is my n value. I'm sorry, which is like, because negative 10 is a third term, so minus 3. Now, of course, we'd want to clean that up and say that, we'd get negative 6n, we'd get negative 10, and then positive 18 up there. So basically, negative 10 and positive 18 makes me an 8 minus 6n, right? So that's what we would clean it up to, but that's basically it. So when you have exponential functions, if you can see the whole pattern, like in this one right here, I can see that, oh, look, I'm multiplying by 3 and it starts at 4. So that's just like an exponential function. The starting value is that guy right there, and then the b is the kind of like the rate of change in a way. So it's like not the rate of change, but it's the thing that you're multiplying by every time, right? So you can see them in these two formats. Well, that's just like what you have right here. Now, yeah, and since we know the initial value, then we're just going to use that. So I'm going to say 4, and we're multiplying by 3. So I like to put it in parentheses just to protect it in case it's negative. And then you put the n up there, right? Now, realize that you can do that with any term. So instead of using the first term, what I could have done is I could have used like a later term, like the 108 or the 36. I would still have to know my common ratio, but I could do that. So that's what this next example is right here. I can use 36 as my initial value in a way, but then I have to realize that when I'm multiplying by 3, that initial value has already been multiplied by 3 a few times. So that's why up here we're doing n minus 2. Because it was a second term, right? So realize that you can change this. You can separate it. You don't have to, but if you want to, this 3 to the n minus 2, that can separate into 3 to the n times 3 to the negative 2, like if you separate it. And 3 to the negative 2 is 1/9. So I basically have right here 36 times 3 to the n times 1/9. And 36 over 9 is 4. So I have 4 times 3 to the n, because it was the same formula as this one right here. Okay, so really it's just to show you that this is the same. Like somebody could write this, but then they could also write this. It's the formula for the same set of numbers. Okay, and so you just have to realize that the formulas can look different, but they can mean the same thing. All right, so down here, just kind of tells you about linear versus exponential functions and whatnot. Okay, all right. So over here we talked about in class how like what you're used to, what you've seen before is like a problem like letter A, and this is going down 2 every time. So that's obviously linear, right? So we're looking for if something is linear, exponential, or neither. All right, so this is linear. So this is linear because over equal length intervals, intervals. So I think we'll abbreviate that letter later, like ELI, right? So over equal length intervals, the output values, or the output has constant change, or the output change is constant. Like it's literally constantly -2. So over here, when I look at this, that's going up by 1, that's going up by 3, this is going up by 5, this is going up by 7. So this is going to be quadratic because obviously you can see things are being squared, and you know the change is changing by 2. The change in the change is constant, but you know the question didn't ask us like to do quadratic, so I'm just going to say neither. All right, on letter C. So in letter C, I can obviously see that I am multiplying by 2. And multiplying by 2 and multiplying by 2. So what we're going to say here, as I showed you in class, is that the change is proportional. So remember that you're going up 1 when you get to 2. So up 1 when you get to 2. Here you're going up 2, but you're getting to 4. So 2/4 is your change. And here you're going up 4, but over 8. So you see how those fractions are 1/2. And so what you say here is that this is exponential because the over the equal length intervals, the output changes proportionally. So this is exponential because over, let's just say equal length intervals, the output changes proportionally. So you have to use this word right here, okay? All right, and so over here, I can see that it is multiplying by 1/2, you know, dividing by 2, same as multiplying by 1/2. So this is basically the same answer as letter C, so same thing. All right, so I would write that again, but we can just be lazy here. All right, so we just have these two little examples here. So let's see. A wild rumor is spreading that Mr. Brennan won 3rd place in the World's Strongest Man contest. All right, Mr. Brennan probably didn't start the rumor. Ha ha. All right, so anyway, the number of people that have heard the rumor can be modeled by a geometric sequence, so that means exponential. All right, 43 people heard it on day 3, so I know that G3 is 43. And 140 people heard the rumor on day 6. So G6 is 140. All right, so this gives me a way to find my common ratio. All right, it might not be pretty because I don't really see a good relationship between 43 and 140, but that's what I'm going to go with. So remember, I used my later one, 140 equals 43, and then the R value must have been used 6 minus 3 times. It must have been used 3 times because I went from 3 to 6. So usually up here I would put like 6 minus 3, but like I know that that's 3, right? Okay. All right. So I got to divide the 43. Now 140 does not divide by 43 very well. So I don't want a decimal really. So I just do 140 over 43 equals R to the 3rd. So my R value is just the cube root of 140 over 43. So remember that the cube root can also be written as a 1/3 power. And since I'm going to take that and use it later on, maybe that would be helpful to me. All right, so the question says, let's see, how many people is going to hear it by day 10? So I basically want to know day 10. So I want to know G10. Okay, so I don't really need the formula. I just need to know G10. So all I have to do is take one of the things that I know and this R value, and I'm going to be plugging in 10. So I'm going to use the G3 and the 43. Okay. No, I'm sorry. I'm going to use this guy right here. All right, so I'm going to use 140. My R value is going to go right here, 140 over 43 to the 1/3. But that R value has to be taken to a power of, remember I am doing over here, I got 10 minus the 140 term, so 10 minus 6. So it's going to be 4. So I'm just going to go ahead and put 10 minus 6. All right, so that's 4 up there. So that 4 up there is going to be 4. Remember, I'm going to multiply my exponents. So I'm going to have this 4 times the 1/3. So that's going to be 4/3. So into my calculator, or Desmos, I'll put 140, and then 140 over 43 to the 4/3. So that's going to be how many people have heard it on day 10. Okay, so you type that in there, and it turns out to 675.6. And so basically 675 people. Okay, so 675 people, because you kind of round to down to the person, because the 676 person hasn't heard it yet. All right, so here in a large theater, rows of seats has rows of seats where the number of seats in each row can be multiplied in arithmetic. All right, so arithmetic. Let me write down a couple things here. So I'm going to have AN equals AK plus D, and then N minus K. That's my arithmetic formula. We haven't used that a lot here. So the 5th row, so A5 is 31, and the 11th row is 49. A11 is 49. So it says determine how many seats there are in the 25th row. I'm going to be looking for A25 later. So I have to figure out my common difference. My common difference. So I'm going to use the later one. 49 equals 31 plus, I don't know D, and then I'm going to be doing N minus K. Well, I was doing the 11th and the 5th term, so 11 minus 5. Because basically we were trying to see, you made 6 jumps to go from 31 to 49. How much was each jump? All right. So solving this here, you get 49 equals 31 plus 6D. So you solve that, you get D equals 3. Take away 31, you get 18 equals 6D, so D equals 3. All right, so then we don't really care about the formula. Nobody's asking me for the formula. I am just trying to figure out the 25th row. So why don't we go ahead and I'm going to use this one right here. So it's going to be 49 for my AK, plus my D is now 3. And then this was the 25th minus the 11th, right? This was the 11th, so 25 minus 11. All right, so A25 is 49 plus 3 times, 14? Yeah. All right, so that comes out to 91, and 91 seats, I should say. Word problem, label your answers. So the 25th row has 91 seats. All right, that is it. Bye-bye.